We continue our discussion on the shortest path problem. In the previous lecture, we explained the shortest path problem using this numerical example. The problem was to find out the shortest distance and the shortest path from 1 to 7. We have already said that this arc weight could represent a cost or a distance or a time. So, we would like to find out the shortest path and the corresponding sum of weights associated with the shortest path. We started with a 0 here, and then we first found out the minimum distance that is reachable from this. So, 2 is reachable at 15, 3 was reachable at 20. So, we picked the minimum and we labelled this 15. Now, from 2 we proceeded to subsequently label 3 at 20, 4 at 25, 5 and 6 at 40 and 7 at 50, and we found out that the shortest path was 1 to 2, 2 to 5, 5 to 7 with total cost or distance equal to 50. We then proceeded to explain a tabular form or a labeling algorithm to do the same thing that we did on the network. This rudimentary algorithm is the Dijkstra's algorithm, and we now present a labeling version of the Dijkstra's algorithm. So, 1 was the source node. So, we start with 1. We write the rest of the nodes here from 2 to 7. We go back to this network to see which are the ones that are directly reachable from 1, and they happen to be 1 to 2 with 15 and 1 to 3 with 20. So, we write 15 and 20 here. 1 4, 1 5, 1 6 and 1 7 arcs do not exist. Therefore, we write a dash here, or we can write an infinity saying that at present the distance is infinity. Now, among these values there are only 2 of them. So, between these 2 we pick the one which has the smallest number, which is 15, and mark it with a star or with some form of a label. Since node 2 is marked, we write 2 here, and then we proceed to this network to find out what are all the other nodes that are reachable from 2. They happen to be 4 and 5. Now, 2 to 4 with 15 plus 10 25, and 2 to 5 15 plus 25 40. So, we look at these values. If you look at 4, now 4 is reachable with 15 plus 10 25. Earlier the distance was infinity, 25 being smaller than infinity, we change this value to 25. Similarly, 40 being smaller than infinity, the value is updated here from infinity to 40. Now, the 20 that was the distance from 1 to 3 remains as 20, because 3 is not reachable from 2. So, 20 remains as 20. Now, we have 3 values 20, 25 and 40, and out of these 3 values we pick the minimum one, which happens to be for 20, and then we mark a label here. Now, since 3 is marked, we write 3 here and then go back to this network to see what are all the things that are reachable from 3, and they turn out to be 3 to 4 and 3 to 6. So, 3 to 4 is 20 plus 15 35. Now, 35 happens to be more than this 25. So, we retain this 25. Now, 5 is not reachable from 3. So, 40 remains as 40. Now, 6 is reachable from 3, 20 plus 20 40, 40 being less than infinity, this infinity value is changed to 40. Now, again there are 3 values, choose the minimum which happens to be at 25, which also happens to be for node number 4. So, node number 4 comes here, and this process is repeated till node number 7, which is the destination node, is labelled and value equal to 50. What we have done here is we have systematically written this, and this labeling version of the Dijkstra's algorithm is far easier to understand and implement if one were to write a computer program to find out the shortest path on the network. Now, the same 50 which happens to be the shortest distance, obviously the same 50 we have got here. While for this we said it is 1 to 2, 2 to 5, 5 to 7, the motivation came from the fact that 0 plus 15 was 15, 15 plus 25 is 40, 40 plus 10 is 50. So, we have a path such that every label for every I j in that path the label corresponding to j is the sum of the label corresponding to I plus the Cij. For example, you could, if we call this as some W2, which is the label corresponding to 2, then W2 was W1 plus C12, W5 is W2 plus C25, and W7 is W5 plus C27. There is a path from 1 to 7, and we got this 50. Now, how can we identify this path from this table? Now, this is something we need to do. Now, what happens is the final value is 50. Now, this final value is 50, there is a change, move upwards, there is a change. So, this change has happened from 55 to 50 because we passed through node number 5. So, the first thing we have to do is write 7, which is the destination, and now since there is a change here from 55 to 50, that change has happened because we have passed through this 5. So, we write 5 here. Now, come back to this. Now, we will be at 5. Now, move upwards again. Now, here there is a change from infinity to 40, and this change has happened because we have moved from 2. So, we write 2 here, and then this is a change, then come back here to 2. Now, here there is no change from the thing. So, 40, then we moved here, there is a change, and this change happened because we labeled this 2. So, we write 2 here, and then we write 1 here. To repeat, we got this 50, there is a change from 55 to 50. So, we represent first the destination node here, then there is a change from 55 to 50. This change has happened because we moved from 5. So, 5 comes here. So, automatically we go to node number 5, which is 40, move upwards. Now, there is a change between this infinity and 40 because we moved from here to the labeled node 2. So, we write 2 here, and then we come back to this 2 and we realize there is no change, therefore, it is 1 2, therefore, the path becomes 1 to 2, 2 to 5, 5 to 7 with weight equal to 50. So, this is how we explain the labeling algorithm for the Dijkstra's and the way to get both the shortest distance as well as the shortest path. Now, what else can the Dijkstra's algorithm do? Now, when we look at shortest path, so far we have seen shortest path from a given source to a given destination. Now, the second type of problem that we can think of is from a given source to any destination, and let us see if the Dijkstra's algorithm can solve this problem as well. Now, if we assume that our given source is 1, now we can easily show that these labels that we have written here not only help us in getting the shortest distance from 1 to 7, we have actually solved the shortest path from 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, 1 to 7. We can show that the shortest distance from 1 to 2 is 15, 1 to 3 is 20, which is obvious, for 4 it is 25, for 5 and 6 it is 40, and for 7 it is 50. So, the Dijkstra's algorithm not only solves the first problem, where it helps us find the shortest path and the shortest distance from a given source to a given destination, it also solves the second problem where it does it for a given source to all destinations. So, with one pass of the algorithm, we have actually solved both these problems. Now, there is a third problem, which is like from any source to a given destination can be seen as the third problem. Now, this can be done in more than one way, one of which is to do a backward pass of the algorithm from here to here. Remember, what we did first is a forward pass from 1 to 7. We can actually do a backward pass from 7 to back, which means, and if we do that, we will be able to find out the shortest distance from every one of these to 7, because a backward pass implies that we are actually trying to find out the distance from 7 to every other node in the network. So, a backward pass of the Dijkstra's algorithm would help us to find the shortest path from every node to a destination, or from destination to every node on the network. The fourth problem is between every source to every destination, which means we wish to find out something from 2 to 6 or 3 to 5 or 4 to 7 and so on. Now, this one of the ways of using this algorithm is to do this: keep every vertex as the source and run it n times if there are n vertices. So, running the Dijkstra's algorithm n times, in this case 7 times, would help us get the shortest path from every source to every destination in this network. So, effectively the algorithm that we have seen actually solves all the 4 of them, but with certain increasing amount of computation and complexity. Now, effectively it solves both these in a single stroke. Given 1 as source and 7 as destination, in a single pass of the algorithm, either through this method or through this method, we can find out the shortest distance from 1 to 7, which is from a given source to a given destination. We can also find the shortest distance from a given source 1 to every other node as destination using the same algorithm. Now, this is one more pass of the algorithm, which is a backward pass, whereas this is a little more complex, where we have to run this algorithm 7 times or n minus 1 times, 6 times as the case may be, so that we can find out the shortest distance from every source node to every destination node on this network. Now, there are other algorithms which try to handle this problem a little more efficiently, where they specifically address this problem, where we find out the shortest distance from every node to every other node in the network. There is a more popular algorithm called the Floyd's algorithm, which we are not going to look at in this course, but nevertheless we understand that we can run the Dijkstra's algorithm n minus 1 times with each of these nodes as the starting nodes, such that with keeping each of these nodes as a starting node and solving this problem to find out the shortest path from a given source node to every destination node, we will be able to handle the fourth one. So, effectively we understand that we can use this algorithm to solve all these 4 problems, though there are slightly more efficient algorithms to solve this. Now, with this, let us come back and try to understand how the Dijkstra's algorithm is optimal, or how do we confidently say that whatever we have done here, or the labels essentially represent the correct shortest path and the corresponding shortest distance. In order to do that, we first formulate the shortest path problem as a linear programming problem, and then try to write the dual of the linear programming problem to understand how these labels work. So, let us write the linear programming formulation for this. So, the formulation will be like this. Now, xij equal to 1 if arc ij is in the shortest path, and is equal to 0 otherwise. So, the objective function will be to minimize Cij xij. So, xij will be equal to 1 if arc ij is in the shortest path and 0 otherwise. Now, if we take this node 1, which is the starting node, now this being the starting node, we should have at least one arc that leaves this node. So, we should write a constraint that x12 plus x13 should be equal to 1, because we have to leave this node in order to reach this destination. So, we can leave this node either through this or through this. So, we say x12 plus x13 is equal to 1. Now, if we take this node, this is an intermediate node. So, the shortest path may pass through this, may not pass through this. This being an intermediate node, the only thing we need to do is to model what is called the flow balance equation. So, if this lies in the shortest path, then you enter and then you leave. If it does not lie in the shortest path, you do not worry about it. So, that is written in the form of a constraint which is like this: minus x12 plus x24 plus x25 is equal to 0. So, what does this constraint do? If this lies in the shortest path, then you have to enter this node, which means x12 should be equal to 1, which also means that you should leave this node by either 24 or 25. So, the constraint will take care of it. So, if x12 is 1, then this contribution is minus 1. So, one of them will take a plus 1, so that you get a 0. Therefore, if it enters 2 through x12, it has to leave either through x24 or through x25. Whereas, if it does not lie in the shortest path, then this will be 0. So, automatically these two will be 0, and therefore, this constraint will take care of that requirement. So, for any intermediate node, all we need to do is to model the flow balance equation. So, whatever comes in should go out. Now, for this node, we will have minus x13 plus x34 plus x36 equal to 0. Now, for this one, we will have minus x24 minus x34 plus x45 plus x46 plus x47 equal to 0. Remember, there are 5 arcs associated with this node, 2 of them enter this node and 3 of them leave this node. For 5, there are 3 arcs associated. So, you get minus x25 minus x45 plus x57 equal to 0. Now, for 6, we get minus x36 minus x46 plus x67 equal to 0, and for 7 being the destination node, you have to reach 7. So, we write x57 or x47 or x67, sum of them should be equal to 1. So, the constraint will be x57 plus x47 plus x67 is equal to 1. We write it in a slightly different way. We write it as minus x47 minus x57 minus x67 is equal to minus 1. Please note that this constraint should ordinarily read as x47 plus x57 plus x67 equal to 1, but we have multiplied this by minus 1 and we have written minus x47 minus x57 minus x67 is equal to minus 1. Now, we have xij is equal to 0, 1. Now, this completes the linear or linear integer programming formulation of the shortest path problem, because xij equal to 0, 1 makes xij a binary variable, and therefore, this formulation is a linear integer formulation where all the variables are restricted to be binary variables. But let us go back and try to understand that this problem is a network problem. We have seen some characteristics of network problems earlier when we have looked at transportation and assignment problems. We also said that transportation and assignment problems have an important property called unimodularity, and because of this unimodularity property, even if you solve the linear integer problem by relaxing this binary variable and by writing it as continuous variable and by relaxing this, we would still get solutions which are either 0 or 1. We have already seen a little bit about this unimodularity property. The unimodularity property would simply mean that the rank of the constraint coefficient matrix, we can actually show the way this matrix is structured. Simple addition of the left hand side and simple addition of the right hand side would give us 0 equal to 0. In fact, one of the reasons we have written this in this form particularly here is to facilitate that. If you add all the left hand sides and all the right hand sides, you will see this 1 and this minus 1 will cancel out, every xij will cancel out to give us 0 equal to 0, which tells us that this is a linearly dependent system of equations. Now, before that, we also observe that this formulation will have as many constraints as the number of nodes or vertices and as many variables as the number of arcs or edges. So, if there are n vertices, we have a linearly dependent system, and we can also show that the rank is n minus 1, and then we also realize that the determinant of the corresponding matrix will have a plus 1 or a minus 1. Because of that property, B inverse will be integer valued, and therefore, the actual values of xij will only be integers, in this case 0 1, even if we relax the binary assumption and treat it as a continuous variable. Because of this unimodularity property, we can ignore the 0 1, treat it as a continuous variable, solve it as a linear programming problem. We would still get values for 0 1 for these variables. One other way of showing unimodularity is that if we have a constraint coefficient matrix such that it can be written in this form, where every variable appears in only 2 constraints with a plus 1 and a minus 1, then we could show that this one is unimodular. So, in more than one way, we can establish the unimodularity characteristic of this matrix. Therefore, we can relax this 0 1 assumption and then treat it as a linear programming problem. Now, once we treat it as a linear programming problem, it is easy to write the dual. So, we start writing the dual of this problem, and therefore, we introduce dual variables W1 to W7, call them W1, W2, W3 and so on till W7. Now, we write the dual of this problem. Now, from duality, once we have defined dual variables W1 to W7, primal being a minimization problem, dual is a maximization problem. It is a maximization problem. So, we will get maximize W1 minus W7, 1 into W1 minus 1 into W7 will be the objective function, maximize W1 minus W7. Now, each variable xij appears in the ith and the jth constraint here. So, if we look at this W1 minus W2, if we look at variable x12, W1 minus W2, we have a C12 here. Now, remember, the primal is a minimization problem. So, dual is a maximization problem. So, minimization problem with all greater than or equal to constraint would give us a maximization problem with less than or equal to this. So, Wi minus Wj is less than or equal to Cij. In our case, W1 minus W2 will be less than or equal to C12, which is 15. Now, similarly, we can write W1 minus W3 is less than or equal to 20. From this, we now start writing W2 minus W4 is less than or equal to 10. W2 minus W5 is less than or equal to 25. W3 minus W4 is less than or equal to 15. W3 minus W6 is less than or equal to 20. W4 minus W5 is less than or equal to 20. W4 minus W6 is less than or equal to 15, W4 minus W7 less than or equal to 30, W5 minus W7 less than or equal to 10, W6 minus W7 less than or equal to 20, and importantly Wj is unrestricted in sign. Now, the unrestricted in sign comes because all the primal constraints are equations. So, dual variables are unrestricted in sign. So, this completes the dual of the shortest path problem. One can also see that the dual has 7 variables corresponding to 7 constraints of the primal, which correspond to 7 nodes in this network. The primal has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 Xij's, 12 variables, which correspond to 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 arcs, 3, 4, 5, 8, 9, 10, 11 variables. So, there are 11 arcs in this network. There are 11 variables here, and these correspond to 11 constraints in the dual. So, the dual will have as many variables as the number of nodes and as many constraints as the number of arcs, where the primal will have as many constraints as the number of nodes and as many variables as the number of arcs. Now, with this primal and with this dual, let us try and get a solution to this problem. So, let us start with W7 equal to 0 that we like to put. So, W7 is equal to 0 would actually give us from here W6 is 20 and W5 is 10 out of this. Now, this would give us W4 as less than or equal to 30. This would give us W4 less than or equal to 35. This would give W4 less than or equal to 30. So, we write W4 is equal to 30. Now, from this we get W3 using this 20, W3 is less than or equal to 40, W3 is less than or equal to 45. So, you get W3 is 40. Now, from here W2 is 35, W2 minus W4 would give us 40. So, this would give us W2 is equal to 35, and from here we have W1 is less than or equal to 60, W1 is less than or equal to 50. So, W1 is equal to 50. Now, if we start with the solution W7 equal to 0 and work backwards, we get W7 equal to 0, W6 is 20, W5 is 10, 4 is 30, 3 is 40, 2 is 35, 1 is 50. So, W1 minus W7, so this W value is 50. Now, we realize that this is a feasible solution to this dual. Now, this is feasible to the dual in the sense that, now if we look at this value, W1 minus W2 is equal to 15. So, this is satisfied as an equation. W1 minus W3 is 50 minus 40 is less than, so this is an inequality. W2 minus W4, 35 minus 30 is 5, so inequality. W2 minus W5, 35, 10, 25 equation. W3 minus W4 is 10, inequality. W3 minus W6, 20, inequality. W4 minus W5, 20 equation. W4 minus W6 inequality. W4 minus W7 equation. W5 minus W7 equation, and W6 minus W7 equation. Now, all this dual feasible solution satisfies all these, satisfies unrestricted in sign, and now we also realize that this is satisfied as an equation, 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 equation and equation. Now, if we apply complementary slackness to this dual feasible solution, wherever it is satisfied as an equation, the corresponding variable is a basic variable in the primal. So, x12 is a basic variable, I am just circling them. So, x12 is a basic variable, 25 is a basic variable, so I am again doing this, 25 is a basic variable, so I am again doing this. Now, 45 is a basic variable, 45, 45, then I have 47 is a basic variable, 47, 47, I have 57 and I have 67. So, these are my basic variables. Now, there are 6 basic variables, which is also understandable. There are 7 constraints, it is a linearly dependent system. So, we will have n minus 1 basic variables. So, there are 6 basic variables. Now, corresponding to these basic variables, can we define a solution to the primal? So, this would give us x12 equal to 1, this is satisfied. Now, because x12 is 1, x12 plus x25 equal to 0, this remember these are non-basic and therefore, they take value 0. So, minus x12 plus x25 equal to 0 would give us x25 equal to 1. Now, as far as this is concerned, x13, x34, x36. So, we go back to this 1 3, 1 is 50, 3 is 40, so inequality, 3 4, 3 is 40, 30 inequality, 4 6 is 30 plus 20 again inequality. Now, we come back to this one 4 5 and 4 7. Right now, we have put x25 equal to 1. So, this would give us a contribution of minus 1. So, we have 4 minus x45 and 5 7 equal to 0. So, this would give us x57 equal to 1. Now, from here you would have x minus x57 is equal to minus 1. So, you will have x47 equal to x67 equal to any one from here 1 3 or 3 4 or 3 6 equal to 0. So, we would have one more basic variable to represent this equation, but then that basic variable would also take a value 0. So, corresponding to this feasible solution, we observe that x12 equal to 1, x25 equal to 1, x57 equal to 1 satisfies the complementary slackness condition and also provides a basic feasible solution to the primal. Now, this would give us z equal to 50, 1 to 2 is 15, 2 to 5 is 25, 5 to 7 is 10. So, this would give us z equal to 50. Now, we realize two things. One is, having written the dual, we have got a dual feasible solution by inspection. Corresponding to this dual feasible solution, we applied complementary slackness. We first found out which are the ones that are satisfied as equation and which are the ones that are satisfied as inequalities. And those that are satisfied as equations, we go back here, we try to identify the corresponding basic variable for those that are satisfied as an equation. Now, from that we observe that 1 to 2, 2 to 5, 5 to 7 equal to 1 is primal feasible. So, in more than one way we can show the optimality. One is that we have a dual feasible solution, we apply complementary slackness and we obtain a primal feasible solution. The other way is to show that we have a dual feasible solution with value equal to 50, you have a primal feasible solution with value equal to 50. So, they automatically, the values being equal, they satisfy the complementary slackness condition and therefore, they are optimal. So, this is a way to understand that we get the same 50 here as the optimal solution both from the primal and the dual of the linear programming problem, and we have got the same 50 here which represents the optimal solution. So, this is a way to show from the linear programming formulation that the answer that you have got here, which is 50, is indeed the optimal solution. But then we need to discuss a little bit more. Now, what do these W's represent? Now these W's effectively represent the labels that we have actually given here. So there are 7 values of W. We also realize that one of them is 0, and then we progressively move towards getting this 50. Alternately, but if we look at this carefully, the 7 labels that we have given here for W1 to W7 are actually different from the labels that we obtained there, because we have W1 is 0 here, W1 is 50 there, W2 is 15 here, W2 is 35 there, W3 is 20 here, W3 was 40 there, W4 is 25 here, W4 was 30. So, you got different values of these labels. Now, is there a relationship between these labels and these values that we actually got? Yes, there is a relationship between these values that we have here as well as these labels, and the relationship looks from this point of view, this is 0 and that was 50, from 7 it is 50 and 0. So, effectively they add up to 50, which is the value of z. But more importantly, the difference lies in the fact that if we had done a backward pass of this algorithm starting from 0 here, then the labels that we would have got would be exactly those labels that we have got here. The only difference is when I have described this part of the algorithm, I have described a forward pass starting from 0 for the source and 50 to the destination. But when I describe the dual here, I started with destination equal to 0 and the source getting the value 15. So, effectively these labels represent the labels corresponding to a backward pass of the Dijkstra's algorithm. So, these labels represent the backward pass of the Dijkstra's algorithm, whereas here we have done the forward pass. We have already seen whether you do a forward pass or a backward pass, you will still get the shortest distance from the source 1 to the destination 7. So, effectively the Dijkstra's algorithm is actually a very nice primal dual implementation of the linear programming formulation of the shortest path problem. Now, there is also an interesting relationship between these forward passes and the backward passes, and we will see that right now. So, here let me the dual actually became, the dual was W1 minus W7 subject to Wi minus Wj is less than or equal to Cij, and then we said Wj unrestricted. So, what we had written here are the 11 constraints corresponding to the 11 arcs which satisfy Wi minus Wj is less than or equal to Cij. Now, we can do one more thing, because this is unrestricted, I can always replace Wj by minus Wj, and therefore, we will write this as maximize minus W1 plus W7 subject to minus Wi plus Wj is still less than or equal to Cij, and then we say minus Wj or Wj unrestricted inside. So, this will lead us to a situation where you want to minimize W7 minus W1 subject to W minus Wi plus Wj is less than or equal to Cij and Wj unrestricted. Now, if we start writing the dual in this form and then expand it and then get the labels, then the corresponding labels that we would have got here would exactly be these labels, which are 0, 15, 20, etc. respectively. So, the whole the nice trick lies in the fact that because this Wj is unrestricted, we can simply replace Wj by a minus Wj and yet retain it, so that starting now with W7 equal to 0 would actually give us the forward pass of the Dijkstra's algorithm. The way we actually did it here, we did the backward pass of the algorithm, whereas in this place we did the forward pass of the algorithm. Nevertheless, we have seen a framework through which we will be able to show, or we were able to show, that the labels generated by the Dijkstra's algorithm were indeed optimal, and that is the most important thing to learn from the shortest path point of view. So, shortest path problem, even though formulated this way, because of unimodularity property, has a continuous variable. We can write the dual, and then we can get a dual solution by inspection and prove that the corresponding dual solution is indeed optimal, provided we generate the dual solution based on a certain principle. And that principle was the same principle that we followed when we generated these labels. If each of these labels represent some dual variables and represent some Wj, then what we did was we made sure that Wi minus Wj is less than or equal to Cij, and then we picked the Wj that was minimum. So, if we are able to do that, then we are intuitively generating a feasible solution to the dual of the shortest path problem, and by complementary slackness conditions it will be optimal. Therefore, the labeling algorithm that we have seen for the Dijkstra's is indeed optimal. Right. The next thing that can happen is, we made one important assumption which was told in the earlier lecture, that for the optimality of the Dijkstra's algorithm, all the Cij's have to be greater than or equal to 0. Now we get into the next question, can some of these Cij's be negative, or can they take negative values? So let us see what happens if some of the Cij's can take negative values. So let us take a simple network to explain this. So let us consider a simple network where the distance here is 10. So this, we call this as 20, we call this as minus 5, call this as 10, and we call this as 5. So let these be the distances that we have here. So we call this as let us say we call this as minus 15. Now if we start the Dijkstra's algorithm for this, we will label this with 0, then we have 1 to 2 is 20, 1 to 3 is 10, so we label this as 10. Then we will do this, 1 to 2 is 20, 3 to 4 is 10 plus 10, 20. So let us say we label here, we label a 20 here. Now we will do 10 plus 10, 20, 20 plus 10, 25. So we would label this as 20 and say that the Dijkstra's algorithm terminates with this. So the single pass of the Dijkstra's algorithm would give us a shortest distance from 1 to 4 as 20. Whereas we know that if we take the path 1 to 2, 2 to 3, 3 to 4, the distance is 20 minus 15 plus 5, which is actually 10 and not 20. So the reason we did not get the correct answer here is because we violated one of the assumptions that Cij has to be greater than or equal to 0. Now can we modify the shortest path algorithm if we have these negatives? Now such problems are called shortest path problems with arbitrary cost. An arbitrary cost would mean either a positive or a 0 or a negative cost. Yes, we can modify this algorithm through this. So what we do there is this. We would first start with, now instead of these labels, let me simply call them as W1. 1 being the source, we call this as W1 equal to 0. We will have W2 equal to infinity, W3 equal to infinity, and W4 is equal to infinity. Now what is the dual of the shortest path problem? Dual of the shortest path problem is Wi minus Wj is less than or equal to Cij. So first thing is, if we are able to find a Wi and a Wj such that or if we write the dual this way, by changing this we get Wj minus Wi is less than or equal to Cij. Now, if we replace this unrestricted variable by the negative of that, you would get Wj minus Wi is less than or equal to Cij. So, if you are able to get an Ij such that Wj minus Wi is greater than Cij, then we can actually correct the Wj. So, if we look at this pair 1 2, Wj minus Wi is greater than Cij. Please observe that we are looking at this particular form of the dual. This is the first form of the dual. Here we got Wi minus Wj is less than or equal to Cij, Wj unrestricted. This form comes because Wj is an unrestricted variable. I am replacing this Wj by minus Wj, which would continue to be unrestricted. So, Wj unrestricted, but you will have minus I plus Wj is less than or equal to Cij. So, we are using this form of the dual. So, here you have an Ij pair such that Wj minus Wi is greater than Cij. So, update this one. So, pass 1 of the algorithm. Now, we have W2 is updated to 20. So, we have W2 is updated to 20. Now, again go back, Wi minus Wj infinity and 0, Wi minus Wj is greater than Cij. So, upgrade W3 to 10. So, W3 is upgraded to 10. Now, here you have Wj minus Wi is infinity minus 20 is greater than Cij. So, upgrade W4 to 25 such that you have Wj minus Wi is equal to Cij in this case. So, now the values are updated from the original values till you get first pass you get 25. Now, go to the second pass and check whether for all ij's Wj minus Wi is less than or equal to Cij. 20 minus 0 is equal to 20, satisfied. 10 minus 0 is equal to 10, satisfied. But come back to this, Wj minus Wi is minus 10 is greater than Cij. So, update this to 20 minus 15. So, W3 is upgraded to 5. So, W3 changes to 5. Now, this one is satisfied. Now, again in pass 3, verify for all ij whether Wj minus Wi is less than or equal to Cij. Wj minus Wi is equal to Cij. Wj minus Wi is less than or equal to Cij. Wj 5 minus 20 is less than or equal to 15. 25 minus 5 is less than or equal to 20. Now, Wj minus Wi is greater than Cij. So, 25 minus 5 is 20, 20 is greater than 10. So, now change W4 to 15. So, W4 becomes 15. Now, once again go back to the algorithm to check whether for all ij's Wj minus Wi is less than or equal to Cij. Now, Wj minus Wi is equal to Cij. Wj minus Wi is less than Cij. Wj minus Wi is equal to Cij. Wj minus Wi is less than Cij. Wj minus Wi is equal to Cij. So, this set of Wj's satisfies the condition Wj minus Wi less than or equal to Cij. Therefore, this value is optimal. So, the only difference is if we have arbitrary costs, if we have some Cij less than 0, then it is necessary to run or modify the Dijkstra's algorithm, so that the dual condition is satisfied by the resultant ones. Now, the first type of thing, which is the Dijkstra's algorithm, they come under the category of what is called label setting algorithms, where you have Cij greater than or equal to 0. Once the label is set, the label will not change. So, these come under the category of label setting algorithms, and the optimality principle is that once a label is fixed, which means I have determined the shortest path from the source to that node, I will not change the label. But when we have arbitrary costs like a negative coming here, then it may be necessary to correct the label as we move along and we apply this duality condition. So, these algorithms come under the category of what are called label correcting algorithms. So, they come under the category of label correcting algorithms. The labels that are set here 0, 20 etc. are now corrected. So, they are not fixed as was done in the earlier case. So, they come under the category of what are called label correcting algorithms. So, this way we can handle shortest path problems even if some of them have arbitrary cost. But then there is another important thing that can happen. Now, let us look at the same network with a slight change, and let us say this cost is minus 40. Now, once again it is very similar to the earlier example, except that one cost, one Cij is negative and it is minus 40, but most importantly it is going to create a big problem for us, because if you look at, let us make another interesting change here. Let me say that let us make this change. So, I would, instead of this 5, let me put this 5, this arc here. So, let us look at a network like this. Remember the changes that I have made. One change is this is minus 40. Here I have changed the direction and it goes like this. Now, the disadvantage with a network like this is, if we look at 2 to 3, 3 to 4, 4 to 2, we have a minus 40, 10 and 5. So, if we look at this cycle has a total length of minus 25, minus 40 plus 10 minus 5. So, this has a total length of minus 25. So, this is a negative length cycle. So, when we have a negative length cycle and we are interested in finding the shortest path from 1 to 4, one will always say that I can start with 0, I come back to 20, I complete one cycle, I get 20 minus 25, which is minus 5, I complete another cycle, I get minus 30, I get minus 55, and it goes on and on and on. So, the algorithm will not terminate here. So, one of the things is, whether you use the basic Dijkstra's algorithm, we ensure that allCij's are greater than or equal to 0. So, there is no question of a negative cycle, whereas in the modified label correcting algorithm, we said if we have arbitrary cost, we can still handle it provided there are no negative cycles. So, there are no negative cycles. So, if there is a negative cycle in the network, then the label correcting algorithm will keep on correcting the labels till it starts getting negative values and it gets smaller and smaller. The Wj's become much smaller and smaller as we proceed. So, the other question that comes is, how do I know that there is a negative cycle in the network? Now, this is a very small network. This has been created only to explain this principle. So, by inspection one can say that this is a negative cycle. But if we are dealing with a very large network, how would somebody know that there is a negative cycle here? So, the answer is, if we apply the label correcting algorithm and then we realize that these labels are becoming smaller and smaller, and then we fix a particular value, like say, let us assume that there is a negative cycle here. So, we would say that if W4 happens to be less than or equal to some minus big M or minus 1000 or some large value that we look at, for this problem 1000 is a very large value. So, look at some arbitrarily defined large value, and when one of the dual variables becomes less than such a value, then the algorithm will terminate, saying that there is a negative length cycle. So, the label correcting algorithm does two things. One is, if there are arbitrary costs and there are no negative length cycles, then the algorithm will terminate by giving the optimum value. If there are negative length cycles, then the algorithm will terminate by saying that there is a negative length cycle, because somewhere as we move along in this, we would have started with 0, 20, so we would start with 20, and after one cycle we will get minus 5, because the length of this cycle is minus 25. After another cycle we get minus 30, minus 55, and so on. Somewhere the value keeps reducing and it will go to less than this 1000, and therefore the algorithm will terminate at that point saying there is a negative length cycle, and the algorithm will not find the shortest path from 1 to n. So what we have effectively done is, we have now shown first of all the primal dual relationship that is associated with the Dijkstra's algorithm. We formulated the problem as a linear programming problem, we wrote the dual of that problem, and then we derived the optimal solution to this problem using some ideas from duality. We first created a dual feasible solution here based on an idea that we kept this as small as possible, so that we finally got to this 50, and then we showed that applying the complementary slackness conditions to this dual feasible solution, we were able to get a primal feasible solution which was optimal. We also showed that there is a relationship between this label and this label, both of them, while this represented the forward pass, that represented the backward pass, and we also said the underlying idea is to keep Wi minus Wj less than or equal to Cij, and then try to keep it as small as possible. As small as possible comes by labeling here, because the moment we know that this is 15, we labeled it as the smallest possible value of 15. We labeled this for the smallest possible value of 25, such that Wi minus Wj is less than or equal to Cij. So we also showed why this is true by redefining the dual this way, so that we actually end up minimizing this, satisfying this condition. Then we extended this idea to look at shortest path problems with arbitrary costs, some places where you have some negative values, and then we modified that algorithm based on this duality principle. We also showed a way by which, if we have negative length cycles, the algorithm will terminate without giving the optimal solution. We will continue in the subsequent class on what are called successive shortest path problems.